So yesterday we introduced the harmonic oscillator, and we saw that we wanted to solve the Schrödinger equation, right? In a way that we can determine both the energy and the eigenfunctions or the wave functions of the system, right? So we deduced yesterday that for the harmonic oscillator, the energies depended on h bar omega naught, right? And this was here 2m plus L plus 3/2 of, which is for the 3D case, which is always the case. All right. So today our goal is to deduce the wave function, because the wave function, as we mentioned yesterday, will provide us with all the information about the system, given the uncertainty principle, the limitations from the uncertainty principle. So basically, we deduce the K scheme or our harmonic oscillator states. This first one was the 3/2 h bar omega naught, has that energy and corresponded to a 0s. Right. The next one was a 5/2 h bar omega naught and corresponded to 0p. The next one was 7/2 of h bar omega naught and corresponded to 1s and to 0d, and so on and so forth. But remember, each level, each harmonic oscillator, this would be for n equal 0, n equal 1, n equal 2, capital N equal 3, right? And this is always the equidistant energy between different levels, different floors. As we mentioned yesterday, this is a building, right? And we are trying to accommodate all these protons and neutrons, and we say that in this one we can only accommodate 2 protons, because for a particular s equal to 0, you can only have proton pointing up, spin up, or a proton with a spin down, right? So for s equal to 0, the occupancy is equal to 2L plus 1. That's the occupancy of each floor, right? So today, our goal is different. We have understood how many of these protons and neutrons can live within the same floor. But now today, we want to deduce what are these fellows here. And what are these fellows here? We are going to call maybe the ground state, we can call it 0. The next state, we're going to call it 1. The next state, 2. Or we call it 0s, 0p, 0d, we could call it different ways, but we're going to call it in a simplistic manner with our understanding of quantum mechanics. And we're going to bring all quantum mechanics here, is that we have a basis, a set of states, which are our basis states, and these are going to be these 0, 1, 2, whatever n, right? And any state, any nuclear state, for instance, a 2+ state, can be described as a linear, well, let's call it 2+, so we don't confuse with the basis states. These are our basis states, right? Any basis state is going to be given as a linear combination of these harmonic oscillator wave functions, right? 1 plus blah, 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 whatever constant we call this one n, right? So alpha squared plus beta squared plus all of them is equal to 1, which provide 100% probability of this state being a linear combination of these particular basis states. Okay, So today our goal is to calculate, as I say, the wave function. And for that, we're going to start working right now. We'll come back to this plot later on, but just for you to see what we're doing. So now, wait for the page to come. Here we go. So then we are going to apply. Actually, I want to multiply this because we're going to have a long calculation. I want to have it in portrait. Yeah. Okay. Let's see if we can zoom here. All right. So actually, it looks better on the other one. So let's do it this way. So we'll move to the right and let's see what happens. So we have a harmonic oscillator potential. We're going to solve the Schrodinger equation. We're going to deduce our wave functions. As I say, we're going to call it 0, 1. Those are the harmonic oscillator wave functions. Today, we want to deduce those. And for that, we know that the Hamiltonian is equal to T, the kinetic energy, plus the potential energy, which as yesterday we defined, P squared 2m plus 1/2 of kx squared, where k is m omega naught square x squared, right? And then we can put here this as a function of h bar omega. We can put h bar omega naught, or we can drop the naught. So which is going to be equal to P. Remember that P is an operator, so it has a little head here. It operates on a wave function. So this will be basically P 2m h bar omega naught plus n omega omega naught, and then we have here 2 h bar of x, right? So 2m right, of x squared, right? So now we define A, the annihilation operator, and we call it annihilation operator because we, from one level, we annihilate that level and we go to the one below. The creation operator will be the other way around. One level, we create the next one. So this A, so yesterday we define, I want to define now as m omega naught 2 h bar to the 1/2 x plus I P square root of 2m h bar omega naught, right? And the same thing we did for A dagger, the same thing, but in A dagger, which is the creation operator, we have that m omega naught 2 h bar to the 1/2 minus I P 2m h bar omega naught, and this is a head, right? Okay, in such a way, if you add them or subtract them, you can change the Hamiltonian into A and A dagger, and that was an assignment. You have to prove that A dagger is equal to 1, the commutator of A and A dagger, by using the well-known uncertainty principle that this is equal to IH, right? So that's Heisenberg's uncertainty principle. And remember that everything has a little head to illustrate that we have operators, but we're going to drop them. So we don't worry about those right now. Right, by using that, we can finally deduce the eigenvalues. And this is your job to do, which yesterday we defined as h bar omega naught 2m plus L plus 3/2. But let's carry on with our definition of A and A dagger. And let's move on and say, okay, remember that P in quantum mechanics is minus IH bar, the partial derivative with respect to X, right? So let's just use A, and then at the end we have A dagger, which will be very similar to, let's substitute all these things in A in the annihilation operator. So basically this will remain the same, and omega naught to H bar 1/2 of X, and this fellow will come here as I, and now we have IH bar delta with respect to X, we divided by the same thing, to MH bar omega naught, right? And this will basically remain as, so as you know, I squared is equal to -1. So minus, so it will be basically M omega naught 2H bar 1/2 of X plus H bar, and here we have this 2mH bar omega naught partial derivative with respect to X is another operator. Okay, so far so good. We're going to try to simplify the definition of the creation and annihilation operators A and A dagger by doing this little bit of mathematics. Let me warm up my hands. So now we are going to assume that we're going to make a change of variable. We're going to assume that beta square is equal to M omega naught H bar. So basically we have that beta is M omega naught H bar to the 1/2. Right, and with that, we can change the whole A dagger and simplify things quite nicely, actually, because that will be beta, the square root of 2. This 2 has come out as a square root of 2. This thing remains beta, and then we have here a X plus H M H bar M omega naught partial derivative with respect to X. And similarly, we have for A dagger the same thing, but for the creation operator, we have beta over square root of 2 X. So we have simplified minus H bar M omega naught partial derivative with respect to X. Okay, so we have reduced it a little bit. We have reduced the complication of the original A and A dagger, but still not to satisfactory conditions. So we are going to make another change of variable. So we're going to change the variable, and we're going to call it this guy, psi is going to be equal to beta square X square, in a way that this fellow is equal to m omega naught h bar to the 1/2 of x, right? So now with this, we are going to substitute, as you can see here already, that this, actually, you can see here that this obviously is this fellow psi equal beta x, which is basically what we have here. And that's why we're doing this transformation. And let's keep doing this calculation for A, and then we go back to A dagger. No, I want this to be landscape because we have more. All right, so we have that A dagger. Remember this equation here, we're going to write it down now. Beta A dagger was beta square root of 2 x plus plus what else was it? Plus h bar omega naught plus what is my cursor here? H bar m omega naught partial derivative with respect to x, right? To make sure it was right, h bar m omega naught partial derivative with respect to x. Right. So now by changing this and making this psi square equal beta square x square, we come to the point that this is equal to be obviously bx. We could just say that, which is equal to beta is m omega naught h bar m omega naught h bar to the 1/2 of x. So now, as I say before, it's interesting to see that this guy, that this psi is beta x, which is basically this here. So we are going to utilize that and say, okay, so what we need to know is what is the partial derivative with respect to x, right? So for this, we're going to apply the chain rule, and this is equal to partial derivative of psi with respect to x, partial derivative with respect to psi. And we have that this is equal to m omega naught h bar 1/2 of, and that's it, of this here. And now we can introduce this here, and then we're going to have something very interesting, because this is going to be square root of 2. And then here we're going to have the psi, which is an operator always. But now let's see what happened, because this was beta. Let's put beta inside, which was m omega naught h bar to the 1/2. That's beta. With the partial derivative with this one of psi with respect to, which comes also in here, right? Which is basically the same, m omega naught h bar and the square root times whatever we have there inside already, which is h bar over m omega naught, and then the partial derivative with respect to psi, right? So you can see this is square root, and basically these three guys, they cancel, they are 1, right? So we end up with something which looks much simpler than whatever we have before. The A, the annihilation operator, is equal to 1/2 1 square root of 2 times this equation here. Right. And that looks much simpler than whatever we have here before, right? So this thing, now we can use it to deduce what are going to be our wave functions in a little bit. And similarly, we have for the creation operator, we have 1 square root of 2 psi minus the partial derivative with respect to psi. Right, and these are equations which are very important. And we are going to apply this together with the fact that A operating on a wave function is equal to n minus 1. So these are in the lecture notes, which I have given to you. I don't remember now if that's the equation, but I think so. Actually, it comes as a. This is square root of n. And we have that a dagger applied on n is equal to the square root of n plus 1. The wave function of n plus 1. This is going to become clear in a little bit, because now we have provided the tools to deduce the wave functions that we were looking in the first place, right? This wave function that we wanted to solve. So now how do we do this? So now that we have reached to this point, I'm going to ask questions because I think we have done a little bit of calculations. Let me see. Oh, here we go. And you can ask me anything at this stage, which is complicated, but basically we have done a very simple calculation. We can go back here. And our goal was to get these wave functions, where is my cursor now? Here. To get these fellows, where each state of the nucleus can be characterized by these basis states, right, as a linear combination of them. So now we have developed the tools to make this happen and basically get all these wave functions here. So we have followed the process, very simple process, h bar omega. So we have defined a and a dagger, considering this, basically we did the square root of all these fellows, right? So we deduce a and a dagger in a way that we can also, as we saw yesterday, have the Hamiltonian as a function of a and a dagger operators. And as I told you before, we need to apply this to deduce the energy. So from yesterday, this is a particular case where we are applying second quantization. We are defining the creation and annihilation operators. This is the creation, and this is the annihilation, or the lowering operator, and this is the raising operator, so it's called. So we apply our ideas of quantum mechanics, and basically we make a couple of substitutions here and here, and we reach these much simpler equations, and these that you need to deduce yourself. So assignments.
Professor,
yeah.
Can you please explain the step on top where you cancel the MW naught over H bar? I don't understand how that got canceled.
Yeah.
Yes.
Okay.
Yes.
So because you see, you have beta, and beta is actually m omega naught h bar to the 1/2, right? So basically, I'm getting this beta. I took beta out, but now I'm getting beta in and multiplying by here, right? So we have m omega naught h bar to the 1/2, which is beta, basically, right? Then we have changed delta. We have applied the chain rule here, and we have deduced that this now can be changed to this here. So that's why we get another of these fellows right there. And finally, we get this, which was there all the time, right? So basically, n omega naught 1/2, n omega naught 1/2 to the square root is n omega naught, which cancel with this guy, right? And h bar square root here in the denominator is basically h bar, which cancel with this guy, right? So then we have reached a point where this easily convert into something which is much simpler to work mathematically. Is that clear? Asile? So basically, we have put beta inside. There was this factor already there. We have put beta inside, which is beta. Then this was the delta psi delta x, right? Here, plus the factor which was there before, this one here, right? So they all cancel each other nicely. It's something very actually quite beautiful. So at the end, you get something which looks like this. What is my cursor again? Here we go. Like this and this, right? Clear, Asile? Did you ask? So let me see if you have any more questions. Chat. Okay. So that is the solution to the problem, but we haven't solved anything yet. So now comes another beautiful idea. And now it's time to apply our knowledge and deduce these wave functions. So now that we have these final equations that we see here. So now we have, let's see, we have A, which is the annihilation operator or the lowering operator, which is defined as 1 over square root of 2. And then this is equal to what we have right here, to psi plus the partial derivative with respect to psi. And also we have the raising operator or the creation operator, which is A dagger, which is equal to 1 over square root of 2 psi minus the partial derivative of psi. This we haven't done it. I want you to do it also. But remember, I want you to do this as well. So there's a lot of calculations that you need to do. I want you to get this, the A dagger as well, another assignment. The more we calculate, the better. So now what do we do here? We are going to apply these conditions. A operating on a wave function is equal to the square root of that times n minus 1. Actually, n minus 1, actually the square root of n minus 1. See, that's right. right? And we are going to apply also that the creation operator is equal, operating on a eigenfunction, on a wave function, is equal to the square root of m plus 1, m plus 1. So where I say at the beginning, we are going to call these wave functions whatever, we can call them right now. This one can be this one, depending on the nomenclature, can be actually 0s, whatever is the. So right now, if we apply this to the ground state, it will be 0s, will be 0. So let's start with the first one, which is the 0, right? The ground state. So, and we start with the ground state in a way, in a smart way also, because we know that A applied to the ground state, or let's call it just to, well, it's going to be equal to 0. So this condition is going to be crucial to deduce our first wave function, which we are going to call 0, or let's call it rho 0. So it's easy to deduce, to calculate when we solve the differential equation. So now we apply it, and we have here that 1 square root of 2 psi plus partial derivative with respect to psi of rho naught is equal to 0. Very simple, right? So we're going to put the so obviously this, we don't need this anymore. So this becomes that this rho naught equal minus the partial derivative of this with respect to psi. Right, so basically we can put this together. So psi, the psi is going to be equal, or this one here, to 1 over rho naught, which is the wave function, remember, the rho naught, right? So now, obviously, this has a very easy solution, which is the natural log of rho naught is going to be equal to minus this one square over 2 plus a constant, right? So this is our wave function, where our wave function now we can apply the exponential is going to be given by a constant here, e to the minus this. And this basically is our first wave function, which we call 0, or we can call it 0s in the harmonic oscillator that we saw here, right? So this fellow, we go back here, and this fellow, which we're calling in different ways, but is the same thing. We're calling 0s. Let's call it 0 because the ground state is the first state, right? Or we call it psi, rho naught is going to be equal to a constant e to the minus this thing square over 2, right? This is what we have deduced right here. So the only thing that remains to do is to normalize the wave function in a way that we get a naught, right? And for that, we are going to apply again quantum mechanics, and we are going to deduce what is that constant, a naught. But before we do that, we have so let me see, what do we have to solve here? Okay, so we know that that one, we're going to normalize between minus infinity and plus infinity is going to be equal to a naught square, because we are multiplying the two wave function. Let me see, where am I here? Here we go. A naught square. So e to the minus psi square, e to the again, the cursor, I lose the cursor. There we go. Minus psi square the psi. Right. So now, by doing this, we solve this this problem, right? And we determine what is A naught. So these are typical integrals in quantum mechanics. And I remember during quantum mechanics, the first term, I sent you a way on how to do this, how to solve these integrals. Long time ago, so probably you don't remember. So, but we can, let's solve them quickly. So we have something which looks like this, right? Minus infinity to plus infinity e to the minus x squared dx, right? So obviously this constant come out, so this is what we need to solve, basically. So let's use a little trick. Let's going to change this to polar coordinates. I will explain you in a little bit how to do this. It's very easy, and it takes 1 minute. E minus x squared dx. So this will be the integral of minus plus infinity to the e minus y squared dy, which will be equal to a minus infinity to plus infinity e minus x squared plus y squared dx dy. And now we apply that r, right, in polar coordinates. So x is equal to r cosine of theta, and y is equal to r sine of theta. And basically, we have that r squared is equal to x squared plus y squared. So this integral becomes from 0 to infinity, from 0 to 2 pi e to the minus r squared r dr d theta. Basically, we are changing to polar coordinates, and now this is clearly 2 pi here, and the integral between 0 and infinity of e minus r squared r dr, right? So easy enough. We can make this, we can put the 2 inside. So we have a pi, and we have a 2 inside, but only we need a 2. We need a minus 2 to have the derivative of this here. So we put minus 2 r, because r is there already, right? This r, e to the minus r squared dr. This is the derivative of this. So this clearly simplifies between 0 and infinity. Clearly simplifies to minus pi e to the minus r squared, integration between 0 and infinity. So between 0 and infinity, we know that the exponential to minus infinity goes to 0. So basically, we have that this is equal to minus pi times 0, and e to the 0 is 1 minus minus. So basically, the solution is just pi. Right? If this is pi, so we have our solution. We can go back here. This will be a0 squared is equal to the integral that we just solved, right? I mean, 1 over the integral 1 over pi, because it's just which is equal. So basically, a naught is equal to a square root of pi. And with that, we go back here, and we have that the first wave function, rho naught or 0s, or is equal to a square root of pi epsilon exponential of that factor here, right? Square root of pi. So basically, the first wave function of the ground state is equal to the square root of pi e to the minus psi square divided by 2. Yeah. And this is the final calculation. And we can go back here and say, okay, this is our wave function, which is the square root of pi e to the minus this, right? And we have the first one. So what do we do? What do we do next? And next is going to be your job.
Sorry, bro.
Yeah.
Isn't that 1 over square root pi? Isn't a naught equal to 1 over square root pi?
That's right. That's 1 over square root of pi. Yeah. A square. Yeah, of course. 1 over square root of pi. Right. So yeah, the same.
When you were calculating, Prof, your pi was negative, and then your final answer is positive.
Sorry, say that again. Here.
When you're calculating there, your equation was negative, and your final answer is positive. Your pi.
Right. Because this is equal minus pi e to the minus infinity minus e to the 0. So minus and minus is plus, right?
Okay.
So these are the and basically you're right. This is the final. Let me just write it down here because it's 1 over square root of pi e to the minus this one, right? So as I say now what do we do? The next step is yours, and this are the assignments for Monday. Well, let's leave this assignment for Tuesday. Or because this is going to be calculations, and then what do we do next? I mean, we apply the annihilation operator on the ground state. So obviously now we need to apply the creation operator on that state that we have already deduced, right? So we know that A dagger on this row knot will be equal to n, which was 0, right? N is 0, square root of 1 is basically 1. And then we have here row 1. So your step, another assignment, is to get row 1, row 2, row 3, up to the point where you get the Hermite polynomials. This must be clear, right? So we are applying, we use the annihilation operator on the ground state, because that we know is going to give us 0. And now we are applying the same thing, but now we are applying the A dagger onto 0, because this is going to give us 1, right? And so on and so forth. We are going to apply A dagger to 1, and we're going to get 2. Actually, a square root of 2 there will be, remember that the general formula is A dagger on n will be equal to n plus 1, I think, square root n plus 1. And then here we have n plus 1. So basically, you are going to reach a way, and now we see the power of the harmonic oscillator, which is that we can easily calculate not only the energies, but also the wave functions, right? These wave functions, again, I go back to the beginning. They're going to be our basis states, and any nuclear state is going to be deduced as a linear combination of these fellows that you are calculating right now. So the assignment is we got the ground state wave function. You're going to get the first excited state wave function, the second, the third, the fourth, for each of these particular levels. Is that clear, guys? Shoki, is that clear? Chat? So basically, we have reached a point where we know everything. We know that this guy is our ground state and has a wave function 0 that we know has an energy of 3/2 h bar omega naught. This other guy, which is a harmonic oscillator 0, n equal 1. We have a 1 here. This is 5/2 of h bar omega naught. And this is what I want you to calculate, guys. I want to use the beam and calculate 1, 2, 3, as many as you can without any Googling. Forget about the Hermite polynomials right now. Forget about anything that may suggest any Googling. I don't want to use Google. I want you to calculate these things as we have done right now, as I've shown you. But right now, instead of using the annihilation operator, we have to, obviously, the beauty of this thing was that we have 0 and we can get rho naught. And now we're going to, boom, always the creation operator on 0 will give us 1. The creation operator on 1 will give us a square root of 2, right? And so on and so forth. Always applying that a dagger on n is equal to n plus 1, n plus 1. And also, I want you to deduce these equations. So this one and this one, a on n, right? I say is equal to n, right? That was the case. N minus 1. So you can see we are lowering, we're going one level below, which we apply this to the 0. So obviously these things were 0. I mean, this. All right, guys, questions now. I want to see if there's any questions here, because we're going to stop solving problems right now. I know it's your turn, to go. Your being must be full. Calculations. Look, I'm going to show you what I have here. I have done this myself. I'm going to show you. Share the screen. Before that, I'm going to share the screen. Actually, let me. Here we go. So you see, calculations, different calculations for today, for later, more and more calculations. This is what I want you to do, right? Fill up your bin and deduce things yourself. All right. Question, guys. Yesterday you asked very nice questions, and today I know there's a lot of calculations here, but as you're going to watch the video, everything is going to become very clear, and the logic is amazing, right? The logic is beautiful. So we are making the changes of variables, right? We're making all this to simplify the second quantization in a very simple form where we can just apply differential equations and solve the problem in an easy way. So you can see this is the power of the harmonic oscillator. that we can deduce the wave functions in an easy way. So when the computer treats them, we are going to have a huge matrix, that we need to diagonalize to get all these energies, to get all the wave functions. And it's good that the wave functions that they are easy to calculate even by hand, right? So most of the shell model codes that we're going to see, and then we're going to calculate tomorrow during the prac, we're going to do some shell model calculations using a shell model code. So tomorrow I'll teach you how to install it. But that's for tomorrow. We're going to keep getting deeper and deeper until we understand everything. Or not everything, because we never understand everything. The more you know that you don't know. That is the truth. But as much as we can. Guys, questions?